Let us verify whether the given set is a group under the given operation. Specifically, the set G containing elements 1, 3, 7, and 9 is a set under multiplication modulo 10. So we have a lot of axioms, not necessarily a lot, but we do have axioms to consider in order for us to say that a given set is a group under the given operation. We also have here a KD table that will allow us to look into the proof of or showing whether the set is a group. It will help us identify specific elements or results. So we can actually start by, of course, when we talk about a group, obviously it should not be empty and the operation should be binary. That would mean, obviously, using we have here G is obviously non-empty, being having the elements 1, 3, 7, and 9. Okay, and obviously non-empty. So we can now proceed into the identification whether closure property holds for the specific operation star. So first, let's define let star be the operation multiplication modulo 10, so that later on we will not be rewriting this from time to time. We just simply need to write or understand what star means. So we have here star B multiplication modulo 10, and let us find out if this is really close using the KD table. KD table allows us to provide the result when a certain element is operated to another one using the star as identified. Take note that we talk about modulo 10, that would mean we're going to look for the remainder when that result of this case multiplication, the product, okay, is divided by 10. So obviously we will have these components now. Hopefully you can actually appreciate this because this would also be used in the rest of the process. So 1 times 1 is simply 1 modulo 10. 1 times 3 is a 3 when divided by 10. Of course, that's 0 as quotient, but the remainder 3. 1 times 7 is still 7 modulo 10, and 1 times 9 is 9 modulo 10. Continuing on the next row, 3 times 1 is still 3 modulo 10. 3 times 3 is 9, but under modulo 10 is still 9. 3 times 7 is 21. When divided by 10, that's 20, right? The remainder is actually 1. And then 3 times 9 is 27, so modulo 10 is 7. Okay, now for 7, by the way, some of us might think of placing just the reflection with this diagonal as the result. Some of us would like to copy 7, 9, etc., etc. But since we are not guaranteed yet that the operation is commutative, we cannot do that. So simply finish the KD table as it is. 7 times 1 is 7. 7 times 3 is 21. Modulo 10 is 1. 7 times 7 is 49. Modulo 10 is 9. 7 times 9 is 63. Modulo 10, we actually have 3. Then 9 times 1 is 9. 9 times 3 is 27, so 7 modulo 10. 9 times 7 is 63, so that's 3 modulo 10. 9 times 9 is actually 81, so that's 1 modulo 10. Obviously, we can see that from this diagonal, we're actually just reflecting. Some of us might also would like to argue that this is really commutative, and we can automatically place the results earlier just by reflection in the diagonal. But again, since for commutativity is not guaranteed for all, this process is okay to be followed. Now, looking into the components of this, we can see that all the results here are just 1, 3, 7, and 9, just rearranged into respective grids depending on the result of the operation, and they are all element of G. We can now say that G is closed under your star operation, which is multiplication modulo 10, because all of these are just the elements of G in itself. So we are now down to the 3 axioms as we have verified already, a binary operation and even the closure property. This is very important because in the first place, there's no it's not guaranteed that it's closed, even if it might seem obvious for some. But of course, you just need to look into that and provide all the details to really show that it's really closed. Now, after identifying closure property, let's now proceed to the first axiom of the group. We are going to check whether associativity or the star, pardon with that, we're going to determine whether star is associative in our set G. Now, looking into the idea of associativity, this might be a little bit tricky for some, because when we talk about associativity, we need to show that just by our KD table here, it's not easy actually to show associativity aside from commutativity, which is easier. For the associativity for KD table is not that easy. You really need to pick three elements and determine whether different groupings or associations will result to same value. But let us talk about here in generalized manner. Some of references would just like to invoke that since the elements 1, 3, 7, 9 are all integers, and multiplication, the usual multiplication, is closed under the set of integers, and we can say that basically we can also say that multiplication modulo 10 is also closed in this G containing integral values. But of course, let's do it like this just for the purpose of discussion. Since multiplication is associative, okay, in Z in general, I'm talking about Z, not yet G, and 1, 3, 7, and 9 are also elements of set Z. Okay? So we can now look into the perspective first of these elements being in Z, and later on connect it to them being element of G. Okay? So I hope that it's acceptable for me to do it like this. Then we can say that A, usual multiplication, this is usual multiplication, right? Okay, this multiplication is the usual multiplication for Z elements. Okay, so 1, 3, 7, and 9 are Z. So we have something like this. Now, if we're going to assume, of course, we can have here for all A, B, and C, you can say here element of G because they are all elements of G as well. Okay, that would mean that we can now say, so if we have something like this, so say for example, if the result of this usual multiplication is congruent to, let's say, D modulo 10, okay, just our given, okay, then we can also say that the other grouping will result to the same value because in the first place they have the same they are just the same when they are considered to be integral values. Okay, then with that connection, since this is true for usual multiplication, okay, and since our operation now is multiplication modulo 5, still uses multiplication but an idea of modulo 5, then we can say now, in generalized perspective, we can now say that A star B star C is just equal to A star the grouping, because if they are multiplied, just multiplication, usual multiplication, they will result to the same value. And then when we have to take that under modulo 10, they will still result to the same value. So with that, we can now say, then therefore, star is associative in G. This means G1 is satisfied. Okay, so we are now done with G1. We, as again, other references would like to invoke this, but we also showed a little bit of understanding being the elements of G as integers and looking into the perspective that associativity in usual multiplication is true or will hold for Z. Now, let's proceed to G2. G2, we are going to have here, let A element of G, we need to find E, or there exists E still in G, such that it will follow the idea that A star E is equal to E star A is just equal to A itself for all A element of G. This is the idea of the existence of identity element, such that if we have any element in G, in this case 1, 3, 7, and 9, when operated with E, or E is operated to that value, it will just result to that value. That means our E is the identity element of G, and this should work for all. Okay, for all elements in G, we only have one identity element. So let me erase it, something like this here, and allow me to copy this KD table, and this will be used later on in further illustrating the existence of identity elements. So if I'm correct, this is actually the star here, 1, 3, 7, and 9. 1, 3, 7, and 9. Usually the process for some is they're just looking at the row and column where the same value repeats, just like this one, and that value would be our identity. But for the purpose of the illustration, using the definition of the identity element for star, we have something like this. We can see that 1 star 1 is just equal to 1. So 1 when operated in itself will just be equal to itself. Similarly, when we have 3 operated to 1, so 3 operated to 1, the result is just equal to 3 in itself. And this is also true when that 1 is operated by 3, okay, to 3. Similarly, 7 star 1 will result to 7, also the same as 1 star 7 based on our Cayley table. And of course, you'll have here 9 star 1 is also equal to 9, which is just the same as 1 star 9. We can see here that 9 star 1 is 9, and 1 star 9 is also 9. So basically, when we operate all of the elements to 1, they will just be themselves rather. So this would mean that this value, okay, this value is our identity element because it doesn't change the value of the element operated into it. So we can say here E being equal to 1, and it's an element of G, okay, obviously, is the identity element for star. And with this, there exists identity element, therefore G2 is satisfied. Okay, so now that G2 is satisfied, and G2 is very important because for G3, the identification of inverses, so let A element of G, we're going to find A inverse, which is also or should also part of G, because if the inverse is not part of G, then we cannot say it's a group. So we're going to find A inverse in G such that it will follow this, that when A is operated to that A inverse, just the same as that A inverse is operated to A, will result to our identity element, which is just equal to 1. So the identification or identity element in G2 is very important for G3. So in short here, if we're going to pick 1 and operate it to something, will result to our identity element of 1. Similarly, when that element is operated to 1, will also be equal to 1. Okay? Similarly, for 3 star, that element must be equal to your identity, or that element star 3 must be the identity. So we have here 7 star blank must be 1, or blank star 7 must be 1. And finally 9 star blank must be 1 as well, or blank star 9 must be 1. Now take note here that the inverses are different, may be different, okay, may be unique for every element. The identity 1 is true for all, but the inverses is true for a specific item. Now look at the Cayley table. When can we identify that? So simply look at the Cayley table and look for the item where 1 is existing. Therefore, when do we get 1, the identity? That's 1 star 1. So it should be 1 as well as here. Therefore, the inverse of 1 is just 1 in itself. Okay? Similarly, next, for 3, okay, this is where the identity is. So 3 star 7 is 1. So 3 star 7, and 7 star 3 is also equal to 1. That would mean you don't need to write the remaining item here because this is just duplication. So let me rewrite this to make it better. So the inverse, okay, inverse of 3 is 7, sorry. And the inverse of 7 is also 3. As you can see, we have different inverses. As for 9, star something would be equal to 1. It's here. So 9 star 9 is equal to 1. So basically, when 9 is also operated to 9, that's equal to 1. So the inverse of 9 is itself. So we can see here that all of these are elements of G. They are still found in G, and we can see that the inverses are unique. So from here, we can now say that since 1, 7, 3, 9 are all elements of G. I'm using the order for the inverses here. Then G3 is satisfied. With G3, G2, G1, closure property, and the consideration of the set being non-empty are all satisfied, then this time we can now say, this is now the conclusion, G, which contains 1, 3, 7, and 9, okay, is a group under your operation star. So it's still dependent on what is your star or how you define your star. Star is, in this case, multiplication modulo 10. So that is how we've determined whether the given set is a group under multiplication modulo 10. We showed all of these axioms, and again, very important, you start with the Cayley table so that you would know the correct forms of results when the operation is implemented into pairs of elements in G. Thank you very much for watching.